6 hours. That is all the warning humanity had before a house-sized asteroid passed closer to Earth than some of our own satellites. No sirens, no evacuation, no advance press conference. Just a rock moving at 15 kilometers per second, discovered by a telescope scanning the sky for exactly this kind of object, and found only after it was already inbound. In the next few minutes, you're going to understand exactly how something that large can sneak up on a planet covered in observatories, why the 6-hour warning is not actually the scary part of this story, and what the real threshold number is that should have your attention. This will take about 18 minutes, and by the end, you'll know precisely what to watch for the next time this happens. Because it will happen again. Start with the object itself. Estimates put it in the range of 10 to 20 meters across, roughly the size of a house or a mid-sized yacht, with a mass that, depending on composition, could sit anywhere from a few hundred to a few thousand metric tons. Moving at that velocity, an object like this carries kinetic energy equivalent to a small nuclear device. Not planet-ending, not even country-ending, but city-ending if the geometry lines up wrong. That is the piece people gloss over. Size alone doesn't tell you the danger. Velocity does the real damage, and velocity was never in question here. What was in question was whether anyone would see it coming at all. Here is the single most important thing to understand about near-Earth object detection. Telescopes are extraordinarily good at finding large, bright, slow-moving asteroids, and comparatively blind to small, dark, fast-moving ones. The math is unforgiving. Brightness falls off with the square of distance, and a 10-meter rock reflects almost nothing. Against the glare of the daytime sky, or approaching from the sunward direction, these objects are essentially invisible until they are almost on top of us. That is not a failure of technology. That is a geometric limitation baked into how light and optics work. You cannot see what the sun is actively blinding you to. Connect that back to the 6-hour warning. This asteroid wasn't missed because nobody was looking. Survey programs run every clear night, systematically imaging huge swaths of sky, comparing frame to frame, flagging anything that moves against the starfield. The problem was trajectory. This object approached from a sunward angle, tucked into the glare where automated surveys have almost no coverage, then swung into visibility only hours before its closest pass. By the time it crossed into a dark observable patch of sky, it was already inside the orbit of the Moon. Detection, confirmation, orbit calculation, risk assessment. All of that compressed into a window measured in hours, not the weeks or months astronomers prefer. Now, bring that back to what actually happens inside a monitoring center during those 6 hours. The first detection generates an automated alert. A moving point of light, catalogued, flagged, for follow-up. Within minutes, other observatories are notified through a rapid response network, asked to point their instruments at the same coordinates to confirm the object is real and not an imaging artifact. Once confirmed, orbital mechanics software calculates a preliminary path. This is where the tension lives, because early orbital solutions carry huge uncertainty. A rock could theoretically be on an impact trajectory, a close miss, or a comfortable distant pass, and initial data often cannot distinguish between those outcomes with confidence. Each new observation narrows that uncertainty cone. That is the real work of those 6 hours. Not evacuation planning, but frantic, high-precision math, refining a line through space until the risk of impact drops close enough to zero that officials can stand down. Consider the historical case that made this exact scenario feel familiar rather than theoretical. In February 2013, an asteroid roughly 17 to 20 meters across entered the atmosphere over Chelyabinsk, Russia, completely undetected in advance. It exploded roughly 20 to 30 kilometers above the ground, with a force estimated near 500 kilotons. More than 30 times the energy of the bomb dropped on Hiroshima. The shockwave shattered windows across 6 cities, injured over 1,600 people, mostly from flying glass, as residents rushed to windows to see the fireball. No one saw it coming, because it approached from the direction of the sun. The exact blind spot survey telescopes still struggle with today. That event became the reference point the entire planetary defense community measures against, precisely because it proved a city-threatening object could arrive with zero warning at all. Compare that to a 6-hour warning, and you start to see the 6 hours not as a failure, but as actual progress. That is why the number that should concern you is not 6 hours. It's the size threshold where warning time collapses towards zero. Objects above roughly 140 meters are the primary focus of planetary defense surveys, catalogued with years of advance notice in most cases, tracked, modeled, essentially accounted for. Below that size, especially in the 10 to 30 meter range, warning time can shrink to hours, sometimes minutes, sometimes nothing at all. That gap is not an oversight. It's a resourcing and physics problem simultaneously. Smaller objects are dimmer, more numerous, and harder to distinguish from background noise, and building the sensitivity needed to catch all of them at long range is a massive undertaking still very much in progress. Let's address the conspiracy angle directly, because it always surfaces after events like this. Some corners of the internet insist a close approach like this was tracked in secret for weeks, hidden from the public to prevent panic, and only revealed once it was safely passed. The evidence doesn't support that. Near-Earth object data is public, cross-referenced by amateur astronomers and independent observatories around the world within hours of any official detection, and the paper trail of when an object was actually found is verifiable. The far more concerning explanation isn't suppression. It's that the surveillance genuinely wasn't there yet for that size and that approach geometry. That is a worse story than a cover-up, because a cover-up implies someone, somewhere, has this fully under control. The truth is messier. Nobody was watching that patch of sky closely enough, because the tools available cannot watch everywhere, all the time, with equal sensitivity. And that brings us to what actually happens if an object like this doesn't miss. Model the outcome for a 10 to 20 meter asteroid entering at a shallow angle. In most cases, it never reaches the ground intact. The atmosphere itself acts as a shield, and the object either burns up completely or detonates in an airburst, releasing its energy as a shockwave rather than a crater-forming impact. That shockwave is still the dangerous part. Chelyabinsk proved that an airburst tens of kilometers up can still shatter windows and injure over 1,000 people on the ground below. Scale the same event over a denser urban center instead of a semi-rural Russian region, and the injury and damage figures climb substantially, purely from broken glass, collapsed structures near the shock front, and the panic response of a population with zero warning. Here is the single most important thing to understand about why 6 hours actually mattered in this case. It gave forecasters time to confirm, with high confidence, that the object would miss. That confirmation, communicated quickly and calmly, is what prevented public panic, prevented resource-draining false alarms, and let observatories redirect attention to genuinely higher priority targets. 6 hours sounds terrifyingly short. In practical terms, for an object this size, it was enough. The scenario that keeps planetary defense scientists up at night isn't this one. It's the version where the trajectory doesn't clear, and 6 hours isn't enough time to do anything meaningful about it at all. So what happens if warning time runs out and impact becomes the likely outcome? Right now, humanity's toolkit is thin but not empty. In 2022, a spacecraft deliberately collided with a small asteroid moonlet, successfully altering its orbital period, proving that a kinetic impactor can measurably change a rock's trajectory given enough lead time. The critical phrase there is lead time. That mission worked because the target was known years in advance, allowing a spacecraft to be built, launched, and navigated to precise impact with margin for course correction. Compress that same defense method into a 6-hour warning window, and it becomes physically meaningless. There is no spacecraft on standby, fueled and ready, for every unknown 10-meter rock that might surface out of the sun's glare next week. That is the gap between what's technologically possible and what's operationally ready. Now here's your numbered checklist. Watch the size threshold. Objects below roughly 140 meters remain the least monitored category, and that is precisely the range most likely to produce a short warning event like this one. Watch the direction of approach. Objects arriving from the sunward side remain functionally invisible to most ground-based surveys until they've already crossed close to Earth, and new space-based infrared missions are specifically designed to close that blind spot. Watch the survey funding and launch timelines for those space-based detection missions, because their deployment schedule is the single biggest lever on how much warning time future events like this one will actually give us. Watch for how quickly official channels confirm or rule out impact risk, because response speed, not headline drama, is the real metric of how prepared we are. And watch the cataloging rate. Right now, the confirmed count of near-Earth objects above the dangerous size range keeps climbing every year, which sounds alarming, but actually reflects improving detection, not an increasing threat. More rocks aren't appearing. We're simply getting better, slowly, at seeing what was always there. That is the honest state of things. 6 hours of warning is not the terrifying part of this story. The terrifying part is how normal that number actually is for objects in this size class, and how much of the sky remains a blind spot even with modern telescopes running every clear night. The forces at work here are not built on secrecy or conspiracy. They're built on the sheer scale of the problem. A solar system full of untracked rock, a detection network still catching up to that scale, and physics that make some approach angles inherently harder to see than others. Consider that the very same survey systems catching city-threatening asteroids with only hours to spare are, right now, actively improving, expanding, and closing exactly the blind spot that let this one through. The next close call may come with 6 hours of warning. It may come with 60 seconds. Either way, the infrastructure to notice, confirm, and respond is being built in real time, and every close approach like this one adds another data point to that effort. Watch the size threshold, watch the sunward blind spot, and you'll understand every headline like this one before the news outlets even finish explaining it. If this kind of planetary scale hazard breakdown is what you come here for, subscribe, because we track these systems, these thresholds, and these near misses as they happen, not after the fact. Like this video if it changed how you think about the sky above you, and share it with someone who still thinks 6 hours of warning means someone dropped the ball. They didn't. They were watching the entire time. The universe just doesn't always give us the angle we need.